have our Alumni Award winner, Jing Xiao, from WPI. And maybe just a little story about Jing. So she's an alum of the University of Michigan. But before we had the robotics department, we had the robotics graduate program, which was an interdisciplinary program across Rackham with multiple departments. And that started in 2014. But many years before that, there was another interdisciplinary Rackham program with multiple departments called Computer Information and Control Engineering. And that is where Jing did her PhD. So she's an alum of the University of Michigan, but not of any specific department. So since she's the chair of the robotics department at Worcester Polytechnic, we decided we should adopt her as a robotics alumna. So welcome back to Michigan. This building wasn't here when you were here. Lots of things when you were here. But we look forward to hearing a little bit about your, journey from Michigan to Worcester and your work in adaptive robot systems.
Yeah, I'm really so happy to be here. I was after lunch, we had a little tour in our North Campus. I went to the ECS building. That was my building at the time. Yeah, so it was still really, really great. And actually, well, I have to say, I'd like to talk about some of my research on adaptive robotic systems in unknown and uncertain environments. And this has been a long-term goal ever since my Michigan days. Professor Dick Voss was my advisor at the time, and he introduced me to this problem of a packing hole robotic assembly so prone to errors because of uncertainty. So that was very difficult, and it's still difficult. I didn't realize it's still difficult to this day. So I was inspired by this seminal work by Thomas Lozano Paris, Matt Mason, and Ross Taylor in 1984. That was how many years? 40 years ago. Okay, for automatic synthesis of a class of compliant fine motion strategies applicable to assembly tasks. So the idea then is, as you can see, this very iconic drawing showing that for a packing hole task, even very simple ones, because of the tight clearance and uncertainty of robot motion and sensing, so you have an simple insertion, but the peg and hole the peg can land in any of these possible situations, contact situations. So their idea is to then start to synthesize, considering all these uncertainty, what's the region for the peg to be in, and what with the winning region, so-called pre-image, to take into account compliant motion. So I was inspired by that and started working on this problem. And later I also introduced this a two kind of stage approach to first generate a graph or a state space for contact configurations we call contact state, contact formations, and then to conduct motion planning, or actually contact state transition planning on the graph. And then lower level is compliant motion planning between two adjacent contact states. So that's a kind of a planning motion on the surface of configuration space obstacle. But this is all offline, and we have to, after that, we do compliant motion control, force and position control to execution online. The big problem is, even for simple geometry, these kind of work cannot be done online. All this planning has to be done offline. So offline is very high computation cost, unable to be online, but still can only work for simple geometry and still subject to uncertainty in contact detection when you do online executions. So more recently, we all know deep learning is used for this type of work, but also with high training cost, with data, time, and energy, and still usually the network can only work for specific tasks. Usually the end-to-end kind of learning works for specific tasks and difficult to generalize. So the the problem for robotic assembly is, can we have a general and efficient online solution, especially for more complex situations, not just a round peg and hole. For that, many years, 40 some years ago, we already have the remote center compliance device to do that for that particular type. But for more general type, all kinds of assembly, then can we still have that solution? So our experience shows that key to that is our efficient representation of contacts, perception with learning, and constraint search. The combination make that successful. So we start with a geometry independent sphere tree representation of objects. We all know a polygonal mesh, right? And to represent arbitrary kinds of objects. Of course, approximation, but still very geometry independent. But sphere tree is an even higher level one and more concise. You can see for the same kind of bunnies and yeah. No. Okay. So yeah, for bunnies and for dragons and with spheres, it's a far fewer spheres can do almost the same kind of thing. So, but more importantly, this is a great representation for general complex geometry and contact situations, because it unifies contact constraints. Expression is all contact constraint all becomes just a sphere to sphere intersection, no matter how complex the situation is. The next thing is we try to combine the force torque sensing, the perception. So combine perception with uncertainty, use learning to capture to capture the effect uncertainty and to give good prediction of contact configuration. So we map the 6D force and torque information to the most likely contact configuration. The red one here is, it could be just from modeling, from forward kinematics and from just the, we have the rough sphere tree model of objects, but even though there's a contact, this may not show as contact because of these inaccuracies and uncertainty. But with this learning, we can capture that, and the predicted, the green one is more likely the contact configuration. And this learning can be done very fast because we do automatic data collection. No simulation here. Real data, real force torque sensor, and we do the learning. When thousands of couples of data could do the work. And more importantly, we call general because we don't have to do that for all kinds of objects, because this mapping is to capture context, not the object geometry necessarily. So the learned network works for different kinds of part mating and work too. But the learning gives you a many-to-many mapping. So you have the same force torque sensing data, may corresponding to two different kinds of contact configurations. So then how do we do that? We try to resolve this kind of ambiguity by constraint search to minimize the simulated elastic energy between the computed contact configuration and the most likely, the computed configuration, relative configuration, could be interpenetration, could be not in contact to the most likely contact configuration, subject to non-penetration constraints. So with that, it worked very well, this combination. This is actual speed, and we deliberately introduce uncertainty in this full packing hole assembly task, for example. And so it results in some contact, and we do this prediction of contact configurations and try to, with the prediction, we can correct it. And this is robust to uncertainty, more than 10 times our task tolerance. And this is the actual framework. So if we have an object picked up and we do a nominal motion to do an insertion, and then a contact happens, we don't know what kind of contact, right? And then we have the measured force and torque. We go through our prediction neural network, and we have the estimated configuration. The best part to start search, we do a constraint search to find the most likely contact configurations, and we don't stop there. We close loop. we use that to compute the contact force and torque. And then we try to match the compute contact force torque with the sense contact force torque. Of course, they are different because the computation has a lot of simplification and inaccuracy and modeling error and all that. But with the force calibration network, we can do that. And if this matches, we go to this next loop, is to try the compliant motion. And if it works, great, we execute compliant motion and we can assembly successful. If not, if the tried compliant motion is not successful, that actually shows the contact state, although very much close to the force torque information, may still be estimated wrong, maybe a local minimum or something. So we'll do the loop again. But this and if when the robot doing a compliant motion and gets stopped somewhere else because the assembly can be rather complex, then we do the contact detection again, and we try to do the whole thing again. So these loops actually can guarantee success because there are only so many finite contact states, and we have already reduced the possibilities to a lot by learning and by constraint search. So this is a very nice, we like in this gear assembly situation, we have a gear, this is large gear, 120 teeth, very complex, right? And small gear with 60 teeth, and they need to mesh well. And we also introduce uncertainty in this. You see, we have a vacuum gripper. The vacuum gripper can grasp the gear anywhere, not necessarily precisely in the center. So that's grasping uncertainty also is there. So all of these uncertainties can be handled in our approach. And the last gear, you see the multiple contacts, and they also move. It's not rigid, not, I mean, this articulated object, right? So the clearance is very small, a quarter millimeter, and the orientation is also small, but the operation is always successful. This is done by my former PhD student, Shichen Cao, and he just graduated this August, and he's now with Meta Foundation AI group. So somehow they all sucked my students. Last year, another student got to Mountain View to Meta. So anyways, so now we have this a great technique to for insertion with sensing to very robustly for tight insertion tags. We say, how about if objects are not known? How about if we do real-time dense packing of novel objects? So yeah, we use RGBD perception to quickly sense object point clouds and build our sphere tree model and estimate object pose. And then we do dense packing planning. That's more algorithmic, right? That's maximizing space and optimizing motion path, and everything's rough. So especially important is this doesn't have to be accurate, but our last step can always handle the uncertainty. So these perception planning execution, they all just in iterations, loops, not iteration, just loops, frequency. So these are concurrent, so it's very, very efficient. When something is perceived, immediately can go to planning and execution, but these modules work constantly. Imagine all the objects in a conveyor, in the assembly situation, not assembly, in the packing situation come in. So the objects come continually, and the perception system works, and packing is done continually. Okay, so for packing planning, it's sequencing, prioritize objects, short, large, and difficult to fit first. And we try to prioritize objects that are short because if you put a large object, long object, that it can create collision with the manipulator, right? So that's just very simple common sense. And large, you want to pack large objects first. And what does difficult to fit means? It means something like this, is if you have objects already packed or just a container, the first objects are easy. And then we have to define the so-called no-feed volume. That is, you don't have the new objects collide or interpenetrate in the model with the old objects. And those are all sphere tree models. So this boundary shows the no-feed volume boundary. But we like objects to be in contact to make it packing very tight. So we do that. We use that to do pose optimization, maximize available space. And that's actually 4D. We consider this no-feed volume is also depending on orientations, right? Different orientation can show different no-feed volume. So that's what we do for packing planning, and that shows some results. On the left side, we have these 3D printed puzzle pieces, but the robot has no idea they're puzzles. They just to show their arbitrary geometry. They don't have to be just polyhedral. They're not polyhedral. But with this, from perception to action and to actually packing planning and to execution in this tight container. So the robot will actually figure out that eventually it is a puzzle to fit everything in. And the last piece is the most difficult, but every piece you can see there's uncertainty, there's some contact, it has to resolve. Okay. And this is again actual speed. This is on the right side, just arbitrary objects we purchased from Walmart. So they're real objects, no model whatsoever. So it's everything based on perception. And there are more objects than the container can fit. So the packing planning has to plan that what objects can be fit. There's a lot of research on packing planning, but usually 2D by computer scientists, usually in simulated environments, usually very similar objects like boxes of different sizes, not arbitrary, right? Not actual execution by robots. So now we considered, okay, let me try to make it, but this is the actual speed. You see, it has to do some estimation a few times to get in. But I can, where's my cursor? Yeah, just make it a little faster. You see, that's again, very fine manipulation here for insertion. Okay, and we also have these multi-layer because this is 3D, not 2D, not planar. So we can do multi-layer kind of packing when there's enough space to calculate the no-feed volume and available space for dense packing. And on the right-hand side, you see we don't use vacuum gripper, we use just parallel gripper. So for packing these tissue bags, they are even deformable. And we model the model to handle some deformation. So deformable objects can be packed too. And also these objects come in piles. They don't have to be nicely separated. So the vision system will just detect the objects and see what the most visible ones and start from there to detect and do packing. Okay, so we did have some comparative study with the recent work. Very few papers address packing novel objects and with physical execution. But there are some work here, and we have we considered that we compare them, and this is all model construction has to be online, and the planning online. This one has no planning; they just pick and place with some already decided plan. But the important thing is the packing density was low. Ours is pretty high. and perception time is down, planning time is down, and execution time, this is higher than, this is not available, this is higher than this one, but because it's a much high density, so it has to resolve uncertainties, and success rate is much higher. So now I started from that because it started from my PhD time, but only recently we got a more general, very robust and general solution. We really can make it work for all kinds of situations. But this is a more recent work, online deformable object manipulation. Again, idea is to just have a perception, just have a, in this case, RGBD camera. This is done by a current PhD student of mine. And this is all done by a very tight perception action loop with no simulation, no object modeling. We know modeling deformable object is more involved, right? And even for linear deformable object, there's so many degrees of freedom. You can make it a highly redundant manipulator, sort of. But we say, how about if we don't do that? So the same program works for any kind of, for these different materials of ropes, and it worked very nicely. And with built-in kind of robustness, because this is the idea. We start with say, we have some description of the task. This can even consider not just pure low level, no motion planning, it's a task planning. It's a different description of task. And we kind of translate this into a sequence of spatial relation transitions between the robots and object, the target object. And then we look at the robot, we use perception to detect if the spatial relation is desired, then we can continue this motion until the task is executed. Or if it's undesired, then there's a corrective motion. You can see in the previous video, the grasping took a few times because this robust to handle errors. And perception, again, use learning. Use learning for segmentation of these deformable objects in that environment. That's a very important piece. And we have two kinds of motion. Perception motion is to adjust to move the robot or the camera in some way to give a better perception. Like on the left-hand side, this is, you cannot see the rear ribbon and finger, and here you can see. So by changing the aspect, this is one kind of motion. And manipulation motion is to then to change the spatial relation of between the objects and robot. In this case, the one ribbon is between the left finger, between the left fingers, and here both ribbons between the left fingers. So that's manipulation motion to change the spatial relation. And so we have this, again, loop from perception to, perception to see if the state is perceivable. If it's not perceivable, we have perception motion, and then we can repeat. If it's perceivable, we have manipulation motion, and then we repeat to finish the task. So here is the task of tying a ribbon on a toy panda by manual manipulation. Again, it's just follow this whole philosophy of perception and action synergy. This one is slower than the assembly, is more complex. Yeah, okay. So I've talked about two kinds of, I'll work on two kinds of manipulation tasks, assembly and packing, and also manipulation of deformable linear objects. So now I want to, they all follow the same kind of philosophy of perception to detect states and with some learning, and then to even a constrained search and complying motion if needed with very contact rich situations, and to finish the task. So now I'm going to just switch gear a little bit to talk about very briefly search exploration tasks, also in unknown environments. So the search of semantic objects in unknown, like domestic indoor environment, and visual coverage of structure, or could be indoor and could be outdoor. So the first autonomous search of semantic objects, we consider autonomous online exploration by mobile sensing robot of unknown environments. And for this type of work, we need a lot of capabilities: mapping, localization, reduce map uncertainty, planning with uncertainty, and so on. Goal forming online, on the fly, and semantic prior, and a lot of related research, right? Active SLAM does mapping and localization, reducing uncertainty, goal forming. We know we have a very strong research here on SLAM in Michigan. Next best view, that's for like a 3D reconstruction purpose, and things also consider localization of the robot, but doesn't really consider planning explicitly. And deep learning, more recently consider mapping and reducing mapping uncertainty, because from mapping to actually the action to the goal doesn't really do explicit planning and use some semantic prior information. And POMDP, that's partially observable Markov decision process, is pretty much the only type of method that's do planning explicitly considering uncertainty. Okay, but it doesn't do these other things. This is another PhD student of mine and graduated last year. So try to fill the gaps, basically. We want to be able to do that. We have to equip the robot with all of these capabilities. And the essential thing here is try to connect simultaneously localization mapping and planning with uncertainty. But with uncertainty reduction. So the red part is the novel part, is this synergy between SLAM and planning, and all use the uncertainty model and do planar parameter adaptation on the way. And we also use semantic prior. For example, you try to find a semantic object. If you try to find the refrigerator, but it sees a microwave, and we use the functional connection to see if this is the Bayesian map, Bayesian network. If you see a microwave, then probably you should explore that area, and refrigerator probably is nearby. So it's not geometric. It's not like this has to be a kitchen. It's functional of the connection. So that makes it more general. For the planar adaptation, we have the Markov decision process of the robot, or I wouldn't say it's not just robot model, it's a robot and environment in this case. So all of these components, states, actions, initial state is initial state, but transition probability, that's the important thing for modeling Markov's decision process, right? Reward and goals. These are, and planning, find optimal policy from state to action. These are all influenced by the SLAM results at the same time. So adaptation leverages SLAM to reduce uncertainties, and the goal forming reward all take into account the increased information of the environment. Goals can be for exploration, for semantic exploitation, using the semantic prior knowledge, or for uncertainty reduction. Okay, so this is just a robot moving in this simulation environment of Matterport 3D, a domestic environment, try to find a table in an unknown house. And so it does all of these things, semantic SLAM, simultaneous localization mapping, and planning under uncertainty, and finally it finds the table. And this is in our lab. It's very messy. So it's impossible if you try to model it beforehand for a robot to move. So have to do simultaneous SLAM and object searching. In this time, we try to find somebody sitting on the chair. It saw a lot of chairs, didn't see anybody sitting on it. They keep on searching. This here shows the semantic map of the meaningful objects, and this is the low-level geometric map. And just a total bot. It's nothing fancy. So it's a very optimistic than usual SLAMs. Usual SLAM, you want to build a map. And here, the goal is not to build a map, is to find an object. But you have to build a map too, because you want to reduce uncertainty. You find the landmark, and you try to find the objects. So yeah, it's getting there. Yeah, and that's it. So we do ablation study of this method because there's no other method doing this kind of synergy of all of that. So ablation without planner update. How about we just do SLAM, and we just do planning, and you can see then our method has a much higher success rate and reduce total time, reduce path length, and because of a great uncertainty reduction in that. Another comparison of ablation study is to compare method without semantic prior information. Without using that, the result is also much worse. And we had some real experiments without using this Bayesian knowledge about the functional connection of one object with another. And the search can just roam around the building, like in this building is forever. It eventually, after mapping everything, maybe it will come back, but that's not very practical. Yeah. So now finally, the last thing I want to just briefly talk about is visual coverage of unknown structure. So this is inspired by, trying to do maintenance of inspection of nuclear facilities. These are hazardous environment. You don't want the people to get in. They want to put an autonomous robot UAV to go into this. And usually it's very old. There's no structure. So the idea is to have a UAV go into that and to try to do visual coverage to get enough images and for 3D reconstruction of the environment to facilitate inspection and so on later. And robot has to do everything on board: perception, mapping, planning, motion with limited resources. And my former PhD student had this idea of using a data structure to manage the ever-growing data of discovery in such a very large environment. So we know usually if you have a robot moving around a UAV, you send something, you put into a grid, right? It's a voxel grid. But if you plan everything in the voxel grid, the problem is how do you do a coverage planning? Make sure you efficiently cover all the area. And that's not feasible, especially if it's a very large area. So the key here is to have this so-called active perception network is a graph to manage the important viewpoints to get the visual coverage in a graph and plan everything in this graph. So the graph grows as robot exploration of the area, but the maintenance of the graph has to be very efficient. So he used something called differential regulation to always focus on the change part of the graph and to update the APN. But updating is not just adding nodes, also reducing nodes, deleting nodes, deleting edges. The nodes and edges already covered by newly found ones with better coverage, better so-called visual information gain to maintain the size of this. And then at the same time, doing a non-myopic APN planner to plan directly on the APN network. And you can see the network is also hierarchical. So there's an organic growth of a cluster of APN nodes and edges. That's a low-level APN network. On the top level, the planning is just connecting these clusters. So this is a traveling salesperson's problem in an unknown environment, working on an ever-growing and changing network. So the key here, again, representation is very important, and adaptation in planning. So this just give you an idea of how this thing works in the simulation. This is real time. So a UAV with a limited field of view, and it started to explore. So it gathered the real map. Real map is the voxel, the grid, but it does all the planning on this APN, adaptive network, perception network. And you can see, and it does the planning also at the same time when it builds the map and maintain the map, or maintain the APN, perception network. So it tries to, it will give a complete coverage. So when this is over when there's no frontier nodes. So everything is seen before. And this is when the robot will go back to where it started to finish this operation. Of course, this looks relatively simple, but he did do this for much more complex environment. The maze is more complex and larger too, and you can see as the voxel grows, also grows this is the low-level map. It has to grow. When in 150 seconds, voxel grows voxel counts grows to 10 to the power of 4, but the edges of this APN is only 800, and in terms of nodes, there are only 150 nodes in this APN. So it grows much more slowly. That shows the concise way of managing data information. So it's like these kind of things are not very sexy, but super important for managing the information. And because of that, planning time can be kept at milliseconds and pretty consistent for iteration, each cycle of operation over the time. And this shows an industrial plant, also pretty large, 33 meter by 31 meter by 26 meter. And the same story as the actual map growth, this APN network grows much slower, and the computation time for APN regulation, for cluster planning, the view planning, and the tour planning, everything, within a cycle is still in milliseconds. This is a warehouse, much bigger, 90 meter by 30 meter, the same story. So there's even some benchmark comparison to the recent, more recent work. And for different resolutions of the map, as you can see, some work just cannot, for only very low resolution, and the higher resolution just cannot handle it because the data to manage is too much for any online operation. And we also had this one. This is really big. This is a work done by a CMU group. There's a big office building there with 130 by 100 meter by 100 meter, and for the height, 4 meter tall. So we had a neck-to-neck comparison with this one. For this is what their coverage is, and this is our work. And the difference is in efficiency. So everything is more efficient. Okay, so that sum up quickly some of the work. I have done some other work, but I think this is these are all in the theme of robust and adaptive robot operations in uncertain unknown environments through online synergy of a perception, representation, reasoning planning, and leveraging task-independent learning. So I say task-independent or general learning. We try to learn them something that the learned network, the capability can be applied to tasks of new objects. So yeah. So that's pretty much what I want to cover for this research part, and a lot of work funded by NSF, especially the NSF Industry University Cooperative Research Center on robot sensors for human well-being, we call RoseHub, and Amazon Robotics, especially about the packing, and so on. APRI is very interested or inspired work on visual coverage.